All right, howdy everyone. Just like the last team, we are a capstone team in the Electronic Systems Engineering Technology program at Texas A&M University. So let's get started. So the name of our team is Dvdt. On our team we have Dakota Kerr, he is our hardware engineer, and we have Vince Rodriguez, the software engineer, David Smith, the systems integration engineer, and then my name is Trent Tate and I'm the project manager. Also on our team is our faculty advisor, Professor Willie, and our customer is Professor Leonard, and he founded a company called T-Star, and then our customer is Dr. Morgan. So this is what we're going to be talking about. We're just going to tell you what we've been what our project is and where we are now and where we're going in the future. So like I said, our sponsor is Professor Leonard. He founded a company called Texas Space Technology Applications and Research, or T-Star. And he worked at NASA for a few decades and started this space company and back in our town where our college is. And he's basically bringing space to Texas. So he's doing it in lots of different ways. And one of the areas he's focusing on is commercializing low Earth orbit, which this is about 250 miles above us right now. It's where the International Space Station is. And the way to get into that market is with cube satellites. These are really small, right here. This is the frame of one. They're really small for taking data collection around while they're orbiting the Earth. And so T-Star, our sponsor, is making one called the TSAT. So that's what you saw in the beginning. It said the TSAT awakens, because we are awakening the TSAT. We're just now starting it up. And so basically what these will be doing is they will be launched from the International Space Station and they'll orbit the Earth. And the main thing to note is that they're just collecting data. They're doing remote sensing of the Earth, taking temperature, different sensors on board. Inside, eventually these will fall, like they're tumbling into the Earth, and so eventually they'll fall back into the atmosphere and they'll burn up in a big ball of fire. And inside the TSAT is specifically T-Star's TSAT is the modular integrated stackable layer. So this is like if you've heard of an Arduino or a TI launch pad, these stackable layers is a computer system. But this one, what's unique about it is that it's space qualified, so you can use it for space projects. So like this board would have, let's say, a power layer that's powering everything and an intelligence layer that does the brains behind everything. So, but one of the layers that's missing is a communications layer, which brings us to why T-Star approached Dvdt, is that they needed a communication system that could fully integrate into the TSAT to ensure reliable communication from the TSAT while it's orbiting down to an Earth station for data collection. So Dvdt is doing this, and currently you can see our picture down here. There's our board on top of the missile stack. And so it's integrating into the missile stack, and then we're running, with our software engineer, we're running a real-time operating system to handle data in real time as it's collecting data. So here's a picture to help you understand it, the conceptual block diagram. So here's the Earth with the TSAT above it. It's transmitting data down to an Earth station. Inside the TSAT is that missile stack, and then it's going to integrate with our new board that we're making. So inside here, we will get power and data from the missile stack through those connectors. We also can have an external power connector and regulate that voltage down to our board, and we can monitor the power. And then this is where the data is actually sent out, right here. This is our radio transceiver sent out, and it gets amplified and then through the antenna down to the Earth station. And there's also an expansion port for the customer to add extra features in the future. So now I'll pass it to Dakota to talk more about the functional block diagram.
So like Trent said, I'm going to go into our system from an overview perspective. Now keep in mind, the interesting part about our capstone design sequence is if we don't make our system work from every functional requirement to its performance spec, then we don't get to graduate. So it's a very motivating process for us. So using the missile stack, we're going to be using 3 layers: the intelligence, power, and communications layer, as denoted in the red. The intelligence and power layer are not within the scope of our project as they've been previously designed. But adhering to the missile stack architecture, we're going to utilize this power and data bus like we've been talking about. As well, on our board, we're going to have the ability for an external connector to take a battery voltage and regulate that on our board for use throughout the system. Now, the brains of our operation is an MSP430 microcontroller, which can be programmed through an 8-pin JTAG interface, while the bread and butter of our project is obviously communicating, so we're going to need some transceiver that's going to communicate at this sub 1 gigahertz level, which will interface with an SPI interface. After it's been sent through our transceiver, we're going to have that go through an RF amplifier, which will amplify our signal before sending it down over 915 megahertz to our earth station, which will be connected over a USB interface to our computer, which will be our base station. To provide flexibility to our end customer, a number of verification sensors can be interfaced through an expansion port, and that will be able to be communicating through a number of digital, analog, or serial communication protocols. Lastly, or not lastly, but our micro SD card storage is being utilized because when you're orbiting the Earth, you're not always going to be able to see where your Earth station is located. Therefore, we're going to be using this micro SD card to store any data that is collected throughout its orbital period. And that will also be on an SPI interface. And then lastly is the power monitoring capability, which we provide just as an additional feature to our customer. Everything you see here makes up our TSAT architecture, while everything here creates our base station. And in the current progress of our hardware, we're able to take our alpha layer and successfully validate every subsection. And we've just recently ordered our beta revision, where we've optimized each subsection as well as shrinking the overall size for its final use. Next, I'm going to pass it along to Vince Rodriguez for software.
All right, so I'm going to give a little bit of an overview of the software that we're running. So as Dakota said, we're using the MSP430 F5438A. We're going to use the RTOS kernel sysbios, which is preemptive and has a heartbeat of 1,000 ticks per second. So what does that mean? So 1,000 ticks per second, we're checking in 1,000 times and making sure that the most prioritized task is running at that moment. And so that's what the preemptive and that's what the 1,000 ticks per second mean. So the current status of our software is we're in beta development. We've met all our functional requirements with alpha software and doing revisions to beta. As you see to the right, we have kind of what you'd see if you open it up in Code Composer Studio. It's all organized in folders, but the most important ones are going to be app, core, and documentation. So under app, that's where the user's task is going to be. So if we're running an experiment and this is what we want to do, that information is going to be under the user's task. Now, if you want to turn a power driver on, if you want to communicate over the expansion port, or you want to know how to do those sort of things, that's going to be under our core folder, and you're going to see function calls that allow you to do all those features. And last but not least, if you've ever written C programming or been in a class with Dr. Morgan, you know how important documentation is. So our documentation folder holds all of our Doxygen documentation. So what Doxygen is it allows you to make an HTML output of all the code that you've written, and it's a really easy and a really nice way to document your code and allow others to see what you've done. So here's an RTOS overview. So the green boxes, communication, health, idle, these are tasks that we've created, as well as the user's task. So the user's task can be more than one task, hence why it's a cloud. So with that, we have a logger function that will allow us to communicate to the SD card. So with that function, we're going to be able to pull data out and also put data in to the SD card. And that function will have sole control of the SD card, so we don't have anybody fighting over, saving or retrieving data. Moving over to the communications task, we have that connected to the TI CC1120, which will generate an interrupt for us every time we successfully sent a packet or every time we successfully received a packet. So that allows us to do is control all the protocols and all the way that we're going to be sending data back down from the TSAT to our Earth station. So we only have about a 5 to 10 minute window to send information down. So what Dvdt has done is we've created this communications protocol that allows us to define exactly how we're sending the data back down. And so hopefully by that we'll be the most efficient and send the most data down that we possibly can. Lastly, we have our health and our idle. So what the health task does is say we're in SPI and something messes up. We're stuck in a loop and our communications task isn't talking to the TI CC1120 anymore. The health task will be able to recognize that. It'll say, okay, this task is in a loop. Let's reset that task and hopefully bring the whole thing back up to operational. And lastly, if nothing is needed to be running, we'll be setting our microcontroller into an idle mode, which will set it to the lowest power state possible so we can serve as much battery life as we can. And now I'm going to pass it on to David Smith to talk about some testing.
Like Dakota mentioned earlier, it's really important that this thing works, because if it doesn't, we won't be able to graduate. And so what we have done is we've taken this out into the real world and done some long-range line-of-sight testing. So from point A to point B is a 1 mile line-of-sight test that we've done, and from point A to point C is an 8 mile line-of-sight test we've done. And so on the bottom here, we're outputting 27 dBm out of our TSAT communications board. This is 500 milliwatts. We attached a 2 dBi omnidirectional antenna, And so the output power at our TSAT was 29 dBm. We expect, the losses are right there in the middle. We expect 7 dB of pointing loss or cable losses seen at 915 megahertz. And then at the 1 mile, you'll see negative 96 dB. And then at 8 miles, you'll see negative 114 dB. And just to give you another number, at 250 miles, which is low Earth orbit, you'd see roughly 144 dB of loss in power. And so on our Earth station side, we were using a 9 dB Yagi antenna. And so with that, our calculated received power values were negative 65 dBm and negative 83 dBm. And so we tested a few weeks ago, and we got all the way down to negative 115 received power, and that was right at the cusp of where our transceiver chip could then sense a signal at negative 115 dB. And so what we've done is we've created a MATLAB scripts and simulations that allow us to put in the latitude and longitude locations of both our TSAT and our Earth station, as well as the altitude of the TSAT, in order to determine accurate values for the path loss, as well as the line of sight distance and the horizontal or Earth great arc distance. And so where this will be important is that at 8 miles, it was difficult to see a line of sight. The curvature of the Earth at 8 miles requires at least one of us to be, a few meters or dozens of meters higher than the other party, just because of the curvature of the Earth. And so Dakota will then go on and talk about what we plan to do to solve this problem of having a line of sight be prevented by the curvature of the Earth.
All right, so we kind of, like you mentioned, we kind of talked about where we are and what we've done, and now we'd like to talk about what we're going to do. We are currently working on a high-altitude balloon launch, where we'll be launching in about mid to early April, which will allow us to get up to 250 kilometers right there on the cusp of outer space, and that will allow us to simulate our finalized environment to a greater deal, as well as these extreme temperature tests that it's a lot harder to simulate here on the face of the Earth, as well as a potential technology demonstration with a local company in Houston that is the actual launching mechanism from the International Space Station for these CubeSats, and they're looking to do a technology demonstration in about mid-June with a turnover date of middle, end of April, and then that would be a 3U TSAT, so imagine something like this, but 3 times longer in length, and then the width is the same, where we'd be demonstrating this technology that we've delivered to our customer. And then as well, through our capstone design sequence, it's a very iterative process where we've pretty much wrapped up our design and are working to finish our development phases, and are now moving into the end of our documentation and hopefully the delivery so we can graduate and be done in April of 2016, not 2017, or else we would be 1 year late on our diplomas. And then outside the classroom, we're working on a number of different things, such as a documentary to create an added level of documentation, something that's a little more interesting to younger students rather than just looking through pages of documentation. We're doing that as well. That's something that you can never skip over, as well as entering into a number of different design challenges, such as the A&M Engineering Showcase and Ideas Challenge and the Texas Instruments Design Challenge, which will garner us some additional feedback from other industry members that will be vital in providing our customer with information that can help them commercialize low Earth orbit. And with that, we'd like to open the floor for any questions.
Okay, any questions?
Yes, sir.
What kind of batteries are you using, and what are you doing for power management?
So I'll let David Smith take that one over.
So right now, I guess the finalized battery system will be determined by T-Star. However, we're looking into using lithium thiol chloride batteries due to their temperature range. They can withstand negative 55 degrees Celsius up to 85 degrees Celsius, and those are the type of temperatures that we expect to see while flying this in high altitude balloon. So we plan on doing temperature testings with those.
What's your anticipated battery life?
So with those lithium batteries, I believe it's 18 amp hours, and so if we're transmitting continuously at the maximum 500 milliamps, we foresee hours and hours of battery life, longer than the high altitude balloon. roughly 50 hours of battery life. And that's not accounting for the times that it will be asleep if it's not doing a task.
And just to clarify, that's for our high altitude balloon test. For the finalized system, there will be things such as solar panels and the rechargeability of the final batteries, but that is not within the scope of our project, but we are taking that into account.
Any other question? What was the most challenging part?
The most challenging part?
Yes.
I don't really like my teammates. So, no, I'm just kidding. The most challenging part is just going from kind of a classroom environment where you're normally told to take this subsystem and then merge it with this, and it's all very straightforward. And then this is just us taking on the persona of a startup company, like the other team mentioned, and it's not cut and dry. You're learning on the fly. You're taking information you learned in your classes and extrapolating that even further, learning how to interface with your customer, being able to manage your customer and work with real life industry partners, and as well as scoping out projects and understanding just how everything plays an aspect together has probably been the most challenging, but also the most rewarding, because it provides us, I think, with our department, something that other graduates don't get to have.
Yeah, I would say almost every problem you have in a class, there's a solution for it already. And there's a key to every problem in the back of the textbook, but with our problem, we had to determine the solution on our own. We started off thinking that we're going to go with this chipset, but then now looking back on it, have a totally different solution than what we originally thought. And so going through that process of determining what solution is the best, and then going forth with that plan.
And the way we overcame that too is by having support. Like we can't just, we've never built a space project before, and so we chose parts from Texas Instruments because they have the biggest supporting staff, and so we could ask them questions about the parts, and they would get back to us. And we had several other older, wise RF kind of experts helping us in this. So we reached out to a lot of people to just figure this out, because it was a very intimidating goal for us at first, but we really overcame that by collaborating with.
And how many more months do you have time to test this?
We have about 2.5 months.
Okay. And who is helping you to test this?
So our advisor, Professor Willie here, he's the CTO of a local Dallas company, as well as some other people we've met named Michael Willett, an RF expert, as well as connections through our department and through T-Star, providing us just with valuable knowledge either from his contacts at NASA or other industry-leading experts, that we've gotten bits and pieces of information to kind of take each piece of the puzzle and put it into hopefully a nice picture at the end that works.
Perfect. Very nice job.
So other college teams and maybe even companies do CubeSat work. I mean, did you look at what they've done? Is it wireless connectivity?
Yes. There's obviously we wouldn't want to just try and reinvent the whole wheel, but utilizing other people's designs, trying to further enhance the aspects of what they've worked on, but also using them as a kind of rough back-of-the-hand check. So most people haven't always done a link budget for communicating to an Earth satellite, to a satellite in low Earth orbit. So reaching out and finding some of that information, doing our technology surveys, and seeing what sorts of link budgets they're getting, what sort of data rates they're able to do, and providing these technology evaluations has helped us in developing our finalized solution.
And I think one important thing too is a lot of the research we've done on previous CubeSats have all been done in the 400 megahertz range, and so we are testing the ability by going to 915 because you get better data rates at that, but at the same time you lose more power over distance. Yeah.
Okay, great. Let's thank our professor.